Good afternoon, everyone. Lovely to see you all again. I've got a bit of a question now myself. We've spent quite a lot of time learning about algorithms, and we seem to have just been going through problems one by one. We've now got a collection of data structures. We've built up a bunch of C techniques, but I'm not really sure what to do now with all of you. We've covered a whole lot of material, and it's unclear to us what's next. Taylor Swift's concert is continuing, so I guess we could always go and see her subsequent performances, but I feel a little unsatisfied. What should we do? Well, we have a few options. We could try and synthesize the things we've been learning this semester and categorize the algorithms that we've been learning, try and put them together, cohere them in a way, and this is probably a good thing for you to be doing as our exams approach, trying to understand the bigger picture of what it is we've learned. So one approach to this would be looking at algorithms by the type of problem that they're solving. So is it a numerical problem? Is it a game we're trying to play? Is it sorting? Is it searching? What kind of problem are we approaching? We could categorize our algorithms by complexity class. So what are all the n log n algorithms we've learned? What are all the linear time algorithms we've learned? Or we could categorize them by design technique. So what was the method that we used to come up with the algorithm in the first place? What was the fundamental insight that made us able to solve the problem? And it's in fact this last one that we're going to spend most of today on, but let's look at the other two for the minute. Okay, so there are a whole bunch of different problem types. If I go to Wikipedia and look at a list of algorithms, you're now equipped to go through this list, pick any one that excites you, and try and understand it. So we can see there are a whole lot of different graph algorithms, a whole lot of general combinatorial algorithms for combinatorial problems. And this could allow us to solve a whole bunch of broader real-world issues. So we could model animal behavior, fill in the holes in damaged photos. We could determine the best way to route a train through a country, knowing that we need to make certain stops. Matching med schools with graduates, all of these things are now you're capable of doing and understanding, looking up a list of algorithms, trying to understand the implementation, assessing it for its runtime complexity, and then matching it to your given scenario. So that all seems to be well and good. You've spent a lot of time and effort, and it's finally paying off. But what we don't have a sense of yet is how design techniques are played into this. So if I've got a new problem, what technique should I use to approach the problem such that I can construct an algorithm that will effectively solve it? So here are a few different categories of design techniques that we'll look at. And this is what we're going to focus on probably for much of the rest of the semester. Not that that's very long, until we get into some really high-end extension stuff in our very last two lectures. So I've got approximation, optimization, divide and conquer, generate and test, and simulation and randomization. And let's go through these one by one and see what insights we can get by looking at these different ways of building algorithms. So our first one is generate and test. And the name is quite suggestive of what it is. Let's start with this problem. Now, David, you've been patiently waiting all semester for this moment, so let's give you a chance. Let's pass this back. Okay, what's this?
It's a...
Have you seen one of these before?
Yeah, you just fill the numbers that make each number appears once each row in a column.
Have you heard of what it's called before?
I'm not sure.
That's fine. It's a Sudoku puzzle. So the basic idea here is that in each 3x3 grid, all of the numbers between 1 to 9 should appear once and only once. Also, for each row of this puzzle, all the numbers from 1 to 9 should appear once and only once. And for each column, each number should appear once and only once. Have I missed any constraints? I think I've got them all. Okay, so that's our goal here. Now, what are some ways of solving this puzzle? If I gave this to you, give me a couple ways that you could consider tackling it.
Well, so I will just get all the possibility of filling out each rows and just put them together and see whether things. Oh, sorry. Let me say that again. So for each row, I will just fill the number for each rows, to make sure that each number just appear once at each rows, and do the same thing for rest of rows. And there's actually some combinations, and I'll just check whether these combinations meet the requirements or not.
So one approach will be like, just fill out everything and check if it meets the requirements. And let's go back to that in a minute, because I don't think we've got a complete solution there yet. So we have a 9 by 9 grid, 9 possibilities for each grid. So can you do the simple mathematics for me? How many different possible combinations of numbers in grids, in cells could I have? So how many squares do I have?
9.
I have 9 in each row and 9 in each column, so how many cells total?
81.
81, yeah. I'm glad we're past high school mathematics here. And so for the first grid, there are 9 possible, for the first cell, there are 9 possible entries. And we have to multiply those 9 possible entries by the 9 possible things that could be in the second, 9 possible things in the third, 9 possible things in the fourth. So what's the equation that gives us the total number of possible numbers, the ways we could fill it out?
81 times 9.
81 times 9? So 9 times 9, 81. So let me scratch that. 9 times 9 times 9 times 9 times 9, 81 times. So what's that? 9 to the power of 81, you got it. So we have 9 to the 81 possible Sudoku grids. This is not excluding the invalid ones. This is just 9 to the power of 81 possible ways of arranging the numbers 1 to 9 in a cell, in a square, in a 3 by 3, arranging those numbers in a 9 by 9 grid of cells. So that is 10 to the 21 possibilities. Now, of course, we do have some constraints. Some of the squares are filled in. And in fact, we know that there's a minimum number of squares to be filled in, because Sudoku also has this rule that each puzzle should have at most one solution, and it must have exactly one solution. Otherwise, we're not playing a very fun game. We will return to the instance where we don't know if there's a solution or not a little later next week. So after we factor this in, we can turn to some research from the last 10 years, which tells us that there must be at least 16 squares filled in order for us to have a guarantee that there is exactly one solution. So we can go to our algorithmics research and do some of these. In fact, we can generate a whole lot of different squares and figure out what is the minimum number of clues that we could have. And this was quite complicated actually to figure out, but a really interesting paper if any of you are interested in recreational mathematics. So what's the problem here? You said that we could try all the different combinations. What problem have we run into?
Well, it's just a waste of time and the space, like for some unnecessary output.
Yeah, 10 to the 21 is really big. And have you ever solved one of these before? No. Have you solved one? It was Ender. Have you solved a Sudoku before? Okay, so how long does it typically take you to solve a Sudoku?
If it's easy, like maybe 3 minutes, 5 minutes.
3 minutes, 5 minutes. And do you try 10 to the 21 combinations?
Typically, no.
Okay, so there must be some faster way of approaching this problem. What do you do to solve them?
Well, typically we look at like one particular line, and then maybe we go through each of the empty squares, and we see, okay, maybe we look at, like, for example, the columns. And if there's like one number which is already in that column, we know it can't be in that square, so we can kind of reduce some of the possibilities like that.
So that's one option. That's a really good one. We'll talk about that. That's two algorithms away. But what's a simpler one? If you have a grid of 9 numbers, do you ever like try putting a number in and see if it works? If you have a harder Sudoku puzzle. And explain to me that strategy.
Okay, well you do some trial. So maybe you put a number in and see if like there exists a solution for that particular one. If there doesn't, then you know that square can't have that number in it. And
so we backtrack. We rule out that possible combination, and then we go out one level and try a new number. So that's going to be our simplest computational solution. So let's try and shrink the number of possible computations we have to do. We could iteratively fill the board and then backtrack. And this gives us an algorithm in pseudocode that looks something like this. So find the next unassigned square on the board. If there are no unassigned squares, if there are no blank squares, well, you're done. Otherwise, for each number between 1 and 9, try that number in the unassigned space. If that number results in an invalid grid, if it violates one of our rules, if it violates one of our constraints, then skip to the next number, because we know that one is not a valid possible solution. If that number does possibly fit in there, do recursion and recurse on the grid, and then repeat this process again and see if that subgrid that already has that number filled in leads to a possible solution. If you return from that function and it didn't work out, then go to the next number, and if you return from that function and it did result in a totally filled in grid, then congratulations, you've solved the Sudoku. And if this process hasn't resulted in a valid solution at the end, we know there are no valid solutions. So while recursive approaches to solving problems will be part of one of our other strategies that we'll look at today, this is also definitely part of a generate and test methodology of solving a problem. So our general approach was generate a large set of possible solutions, in fact generate all possible solutions, and when we say all possible solutions we can narrow that down, so we can say, well, when we say all possible solutions we really mean all possible valid solutions, and we can fill in some extra information there, and try them all, and if we find the one that works, great. If we haven't found the one that works and we've tried all the possible valid solutions, then we know that it doesn't work. So this is one very powerful technique, generate and test. Okay, so we could do our generate and test a whole bunch of different ways. So we had our first way, which was try all 10 to the 21 combinations. Not so great. We've got this backtracking algorithm, which further reduces the number of solutions we have to search. And I haven't yet found out how many there are, but if you go online, there might be an interesting research paper on it. But we also have another method that's pretty common in programming, and it's one I want to introduce you to, which is constraint satisfaction and its accompanying technique called inference. So what we've been talking about quite a lot in the last little bit of discussion is this idea of constraints. Things that we know that limit the scope of possible solutions. And we could write them down either in broad terms or in very specific terms. And we'll see how we can write them out in excruciating detail in a minute. But if we've written out all our possible constraints, then what we can start to do is make inferences. So Endo, this was your second technique. So explain this to me in a little more detail. Let's say I have a grid, a row, and it has the number one blank square, and it has the numbers 1, 2, 3, 4, 5, 6, 7, 8. What inference can I make? The last one must be a 9. So great logical leap. And if we can teach our computer to make these kinds of leaps as well by using logical statements like the first cell has a 1, and the second cell has a 2, and the third cell has a 3, and the third cell has a 4, and each of the numbers 1 to 9 must be represented, then we can hopefully do some programming to get it to figure out what the missing number is. And this is the strategy of constraint satisfaction and inference. So to look at a demo of how this is going to work, let's pick one of our 3x3 mini grids. The big version is going to be too complicated for us for now. And let's make up some variables. So we can make up a variable for each possible square, and the variable is going to say whether that square is filled with a given number or not. So in location 0, 0, we have a 9. So let's make a variable 0, 0, 9. And we'll set 0, 0, 9 to be true, a 1. In square 0, 1, we have an 8. So let's make the variable 0, 1, 8 be 1 as well. And then we also have a 6 in the corner, and this is in square 2, 2, so variable S226 will also be 1. Now, unfortunately, this is going to lead to a lot of variables very quickly, because even just for these 3 squares, we're going to need a lot of other variables to say all the things that it's not, because our computer program doesn't yet understand that you can only have one number in a square. So we can write it out this way. And this, mind you, is only for 3 of the cells out of our 9 cells in the picture. So we can say that square 0, 0 does not have a 0 in it. So that's the very first one. And it's also the case that square 0, 0 does not have a 1. And it's also the case that square 0, 0 does not have a 2, does not have a 3, and so on and so forth, all the way until we get to the end, square 0, 0 does have a 9. But we're not done yet. So we have to say that square 0, 1 does not have a 0. Square 0, 1 does not have a 1. Square 0, 1 does not. Okay, I'm getting tired of this. And this is just for our starting assignments to represent the 3 squares that we already have information about. So this big conjunction, a joining of all these different logical statements, all these different variables, is our start. We know that this statement is true to begin with because those are just the numbers we begin with. Now, once we have our starting conditions, we want to solve some larger problem. And our larger problem is going to look something a little more like this. So for square 0, 2, so first row, second square, so that's our square in that top corner over there, which of these variables is 1 and which of these variables is 0? So we all know for sure one thing about this, or we know a couple things. Tell me a couple things that are true about this big conjunction statement over there. We're talking about the top left, the top right-hand corner for you guys. Okay, maybe let's pass it to Ruben.
0 to 8, 0 to 9, and 0 to 6 have to be equal to 0.
Okay, so they're all going to have to be equal to 0 because of the inferences that we've made. And we know that at most one of these can be true. So we're going to have to encode these conditions on our logical statements as well. So let's put together all the constraints that I told you about how the game works. And this is going to get complicated fast. So the first says is that there is at most one number in any cell. So for all combinations of y and z, and for all combinations of I, where I is not equal to x, and for all values of x, it must be the case that you can't have a variable being true for a given cell, that you can't have two variables that are true for the same cell. So for example, if my cell is 0 to 1, if my cell is 0, 2, I can't have 0 to 1 being true and also 0 to 2 being true. And the way I represent it is by saying that it must be the case that one of these two variables that point to the same cell are false. It has to be the case when I've solved my problem that for any pair of variables that point to the same cell, at most one of them can be true. Okay, next I can have a condition. Each number appears at least once in each column. And you can see that for x, y, for all combinations of y, for all combinations of z, there must be at least one of the x's that is true. Now remember, we did our bit shifting last time, and we said if I have two variables a and b, and if one of them is true, then the result of an OR is true. So this is doing the same thing, saying at least one of these ORs must be true. Then I can do the same thing for the columns. And then I've got my most complicated one to write out, which is saying that for each 3 by 3 grid, each number should be 1 to 9 appears in each 3 by 3 grid. So ignore my mistake there. Each number 1 to 9 should appear in the 3 by 3 grid. And all I'm doing here with my 3i plus x and my 3j plus y is representing the rows and the columns of each grid. Whoa, now that was a lot of work. Does anyone have a guess of how many clauses this will result in if I want to generate all my constraints all together? Ruben, you've still got the microphone, don't you? So what do you think? This is just a guess.
I've got no idea, but it could have some, like there's 4 different things we've got to check, and it's 9 numbers, so I don't know, 4 to the power of 9 or something?
But we've got to do this for every cell, and there are 81 cells.
Oh, I thought we were just considering...
Oh, so for our 3 by 3, yeah, we've got a smaller number.
Like a really big number?
Okay, really big, what do we think? Scale?
It's manageable, like you can check it for every number.
Okay, so we've got 11,988 clauses. Now this is still pretty hard to solve because for each clause, we've still got the same number of variables that we had before. So while we've broken it down into nice chunk-sized logical statements, we still haven't made very much progress. And it turns out that there is something fundamentally hard for a computer about doing Sudoku. Now we can narrow our search space, we can write our program in different ways, and each of the different ways of writing our program are in some deep sense equivalent because they're solving the same problem. But there's something difficult here going on fundamentally. And we'll talk about this more in our final week. So Ruben, do we want to, maybe Nadine, do you want to take the microphone for a little? Okay. So we've seen a bit of generate and test. What were some fundamental limitations that this approach had? Thinking beyond just Sudoku, what's the problem with generate and test?
Because it takes a long time.
It takes a long time. Why does it take a long time? Yeah, because we're trying out all the possible solutions. So other than that, can you think of any issues? Where isn't going to work at all? It works well for Sudoku. What's a scenario in which guessing and checking is really not going to work?
If there's no mass.
Yeah, if there's not a clear space from which to generate solutions in the first place. So for example, if I ask you, how long will it take the rocket to fall down to Earth, assuming that I launch it at 7 kilometers per hour or whatever it is, that's a very slow rocket. That's going to be very hard to actually calculate the time because it could be any possible time after the time at which you launched it. So that's not really an appropriate technique. The solution space might be too big, so the all possible times after which the rocket is launched is a really bad way to check when a rocket is going to land. In fact, the solution space might be non-enumerable. There might not be a way for us to figure out all the different possible things. Like with the rocket and time, it could land at time t, let's say the rocket launch was at time t equals 0. It could land at time t 0.0001, 0.0002, 0.0000. In fact, there are an infinite number of times after the rocket's launched. So the space is non-enumerable. It's infinite. So totally the wrong approach for that. It might be hard to explore the solution space in a way that makes sense. So with the rocket one, at least we'd say, well, it'll probably, if it's going to land at all, it'll probably land somewhere in a human lifetime, or at least before the end of the universe. So that at least puts a cap on it. We know we should maybe explore outwards from the time of launch. But there are other problems where we don't even know in which direction to look for a problem. And then it also might be slow to check potential solutions compared to constructing the correct one in the first place. So if I give you a computer the problem of solving 7 plus 3, this is probably the wrong approach. There are faster ways to compute 7 plus 3 than trying out all the integers and see which one makes the equation work. So we have some limitations here. Great, that was our generate and test. Maybe we should move on to some other strategies. So we're up to a divide and conquer strategy. And the basic idea here is take a problem, break it into smaller chunks, solve each chunk, and then combine the chunks. So can you think of any divide and conquer algorithms that we've studied?
Yes, one of our sorting algorithms.
Okay, which one of our sorting algorithms?
No, binary search, sorry.
Okay, binary search kind of works. Break it into chunks, solve one of the chunks. But we're only solving one of the chunks in binary search. Are there any that we're solving things on more than one chunk? Quicksort. Any other algorithms?
Yeah, there would be. It's kind of
What other sorts did we do?
insertion sort.
Did that break it up?
No.
Bruce is dying. Well, what's the answer?
Is it sort one? Merge sort?
Merge sort. Yeah, that was a really good example. Don't worry about it. There are a whole bunch of things that we've learned that actually use this. So our longest common prefix, quicksort, binary search, although that only solved one of the parts, we didn't really need to combine the answer after, and merge sort. Now, the nth Fibonacci number is also a really interesting one of these problems, but maybe if we have a bit of extra time, we'll talk about that later. So this is our divide and conquer strategy. It typically uses recursion, at least in the way we think about it, even if we might implement it using iteration or a stack or something different. So that's the end of that technique. We've studied it to death. Let's move to something different. Simulation and randomization. So maybe with our rocket problem that Nadine said was not an appropriate fit for generate and test, maybe simulation is better. What do you think? Seem reasonable? How would you simulate a rocket launch? Do we know any rules that the rocket obeys? Physics, okay. That's a good start. We can use physics to simulate the rocket, and if we know the physical laws that are going to be relevant to us, then we can calculate the change of our parameters at a given time and use that to get an answer to our problem. So part of this is that in some instances, we're going to need to also use randomization to do our simulation because we don't actually know how the world will change. It's great for physics, but if we're trying to figure out, say, how much money you'd make by playing roulette in a casino over and over and over, we're going to need some way to generate random events because we don't actually know the next event. If we know the distribution, however, of the events that we're trying to measure, we can get the computer to generate randomness, and from this randomness, fit it into our distribution, and from our distribution, figure out our outcome, and then map all our outcomes and see where they land. Now, this is actually part of my research interest. One of the things that I did a lot of studying on was random number generators. And surprisingly, you can actually use random number generators to solve a whole bunch of problems that don't seem intrinsically random, and we'll see this in a minute. But just one short aside on what my interest is in random number generators. Random number generators are also critical for cryptography, that is, for securing information on the internet. So if Alice sends something to Bob, and Eve is able to connect to the cable that Alice has sent something to Bob, we want some way to protect the message that Alice has sent. And it turns out that to do this properly, you actually need randomness. And my interest is in what happens if that randomness has been generated in a way that's not very good. Can we find problems with the algorithms and use those problems so that we can spy on people? And even more than that, what are the different problems that governments might have found that allow them to spy on citizenry as a whole? So maybe we'll get a little time to look at that in the very last week of semester, but if you're interested in it, feel free to have a chat with me after. But we can also use it for solving problems that don't seem to have anything to do with randomness at all. So surprise, surprise, you can actually compute the value of pi by taking a square and centered at 0, 0, inscribing a unit circle there, plotting a bunch of random points, and then just computing the ratio of the points. That's enough to give you a fairly accurate value of pi just by simulation. And this is pretty amazing because it didn't naively seem that there'd be some method of calculating pi using such a technique. Now, it turns out we can do this in C as well, and it's not that hard. The only problem is that C's functions for generating randomness have never been particularly good, and so we're going to need to help out the programming language a bit. But fortunately, as time goes on, the C standard library and the operating system functions that generate randomness have gotten a little better. So we could use the operating system's way to get random numbers, or the C programming language's way to get random numbers. And that'll be sufficient for our purposes today. There are also mathematical and algorithmic challenges in actually generating these numbers, particularly when we want to do it uniformly from a range. And as an extension, have a bit of a think about like where might some of these problems be? What are the challenges in generating randomness? But with that, we're ready to take a look at some C code that'll actually do exactly the procedure that we saw. I think, here we go. And this is Monte Carlo Pi. This is one of the programs that is not from the book, but from me. So I'm not sure what that print bits function is doing. The first thing I'm going to do here is I'm going to do what's called seeding the random number generator. Now, computers don't really know how to be random. If I tell the computer, do something random, Computer's going to give me a strange look. What I can do, however, though, is mix a bunch of things together that are unpredictable, and we call this pseudo-randomness. So for example, the time that I turn the computer on is kind of pseudo-random, because, I mean, we don't know, none of us know exactly when I turned it on. For all intents and purposes, that might be random. Now, there are definitely cases where kind of random like that is not random enough, but let's take that. Now let's also mix it with the last time that I moved the mouse. Let's mix that together with some random data that I got from the internet. And maybe, you know what, maybe I'll even buy a little randomness maker and I'll plug that into my computer. And that will measure how often an atom radioactively decays. Now that's pretty random. And we'll mix all these things together and use that to generate our computer's randomness. But given that I don't have my fancy quantum randomness generator here, I'm going to say, you know what, computer, you can use a deterministic algorithm to generate a random number, but I want you to change where that deterministic algorithm starts on the basis of the time right now. And so I'm going to use this time function with a null argument. The null argument says, give me the time right now. And I'm going to use that to seed the random number generator, to tell it, you know what, I know you're deterministic at heart, but instead begin your sequence generation from this particular point, determined by the current time. So at least that'll give me some better sort of randomness. Now I'm going to put myself in an infinite loop. And I'm going to generate some random numbers. And now to ensure that the random numbers are in the right range, I'm going to do some complicated bit twiddling stuff. If you want to actually analyze the program and figure out what it does, ChatGPT explains these lines better than I have time for. So feel free to put that in. So all of this is doing is it's giving me randomized numbers that are distributed uniformly between 0 and 1. And now what I want to do is check just, do they fall in the square that we saw before, or do they fall in the circle? And the way I do that is by calculating the radius of how far out the point is from the center. So if I was going to use the point and draw a line from the point to the center of the circle, is that line less than the radius of the circle in our picture, or is it greater? If it's less than 1, then it means it's within that circle that we circumscribed within the square. And if it's bigger than 1, it means it's outside. And I am then going to print this at a given number of iterations and just show as time goes on that hopefully this will converge to pi. And given that I haven't bounded this, it's just going to keep running and running and running and hopefully giving us a better and better approximation. So let's give this a run. And we can see for each million iterations, pi is converging hopefully closer and closer to the true value. Now, of course, we know that we're limited in some sense because we've got finite precision. As well, we might be limited by the randomness, although in this case, that's unlikely to be the limiting factor. And we see, yep, now we've got 3.1415, which is in fact the correct digit of pi. We're still having trouble with our next digit then. Oh, no, our next digit still hasn't converged. But if you run it long enough, it's quite likely that you will get another digit of precision there. It's going to take too long. OK. Now, what are some issues that we might... Oh, let me switch back to here. Who's got the microphone at the moment? Oh, and you want to run it off to someone else. You can pick your victim. OK, Bella's next victim. What are some problems that we might have with this randomness method? Where is it going to be good? Where is it not going to be good?
You might need a lot of, you might need a lot of time to run it. So I guess depending on how big the problem is, like how long it takes to get accurate enough.
Yeah, so we're worried about the speed of convergence.
Yeah.
What other things might we worry about?
I don't know why that square circle thing works, but whatever that reason is, it might not work for other things, right?
The square circle thing works because if we know about the uniformity of where we know we can generate points uniformly within a range, and then we know that there is a relationship between points that fall in and points that fall out. And that relationship is determined by the area of the circle proportional to the area of a square, and we know that that is proportional to pi. And so if we then count up the points inside the circle, the points outside the circle, we know that those two must be proportional to pi. So we just figure out the proportion, which was a multiplication by 4, and then using that ratio, that gives us the answer. So you do have to know that in advance. So we had to come up with some kind of reason that a randomized solution might work. And it's not immediately obvious to us in any solution why a random algorithm might solve a problem. And this is one of the exciting things in algorithms is you don't always know what approach to take. You might have to try it, think about it, see what works. So as Belle said, we have an issue with convergence. In fact, it might not terminate at all. It might not get close enough to the answer in a reasonable time. And there's also a chance of incorrect results because we're relying on probability and randomness. Both of these can pose problems depending on our needs for the algorithm. This is called a Monte Carlo algorithm because we don't know when it's going to terminate or if it's going to converge. However, there is another type of randomized algorithm that might help solve some of our problems. And this is called a Las Vegas algorithm that always terminates with a finite runtime. However, with terminating with a finite runtime, it may give us a limitation on either how accurate it is or whether if it's accurate at all, it might just give us something that we can still bound with a certain error. Yeah?
With the one you just did with pi, we already know what pi is, so we know if it's right or not. If you already know the answer, what's the point of running that kind of an algorithm?
So
How do you know if it's accurate?
So it's not really that important to run algorithms for which you already know the problems, but in this case it was just instructive to show you that it works.
But like, how would that work in a real life scenario? If you don't know the answer, how do you know if the algorithm's accurate?
Well, if you're confident in your code and you can bound the probability of various different things, so if you know a bound on the probabilities, so for example, you could say there is a 1 in 100,000 chance that my algorithm is off by more than 30%. That could give you enough confidence to make real life decisions. So there are two different, yes, Bruce?
Why is it called Las Vegas?
Las Vegas and Monte Carlo are home to two of the world's biggest casinos. Yeah, and so they're just named after randomness and chance. As to why they're specifically Las Vegas and Monte Carlo, like what's the history behind it, I don't actually know. But in general, it's because of the casinos there. So that takes us through randomized algorithms, and it turns out you can do all kinds of cool things with randomness, like figuring out whether a number is likely to be prime or composite with very, very high probability. You can do primality testing, which, did we see that this semester? No, maybe I skipped that little bit of the class. We can get to it next week if not. But there are a whole bunch of really cool things you can do with randomized algorithms that you might not naively have thought had much to do with randomness. Okay, next category of solving problems is approximation. And approximation, the goal here is to solve a simpler version of the problem that approximates the actual problem that you really want to solve, but with a known error or a converging error. So as you solve the simple problem, you get closer and closer and closer to the original harder problem. Can anyone think of something that you might do in real life that follows this? Belle, you've got the microphone still. No? You want to pass the microphone off?
So for example, you're guessing the square root of the number.
Ooh, you've jumped too quickly to a nice algorithmic one. What about in everyday life?
How long it takes me to get to school.
Okay, how long it takes you to get to school. So what's your process there?
I guess maybe what I can do is I can kind of assume a worst case scenario and a best case scenario. It needs to be bounded between those two.
Okay, that's not a bad one. A nice simple one is imagine you're a parent trying to get your kid to be quiet. If you can get your kid to be quiet for 2 minutes, then maybe you have a better chance of getting your kid to be quiet for 3 minutes, et cetera, et cetera. So it's just a general concept of solving a simple version of a problem that'll help you make some progress towards the final problem, and then potentially you can progress from there. So this turns out to be really, really important in lots of different places. Some of the really big places are in physics, where we might do numeric integration, so trying to solve integrals by approximating it and then getting closer and closer to closer. Doing particle physics very often involves using this type of technique, or solving differential equations. So this is very, very important in physics and chemistry. And we call the field that studies these type of numerical problems that we can solve by approximation numerical analysis. So as we just heard, one kind of problem that we might want to do is computing roots. So it was David, you said that, right? Yeah, so you were right on the money here. If we want to compute roots, we might use an approximation method. So let's look at one particularly well-known approximation method. This is the Newton-Raphson method. And it says in general, it says in particular for calculating cube roots, if you already have a guess for what the cube root is, and it doesn't matter what your guess is, then you can calculate a new guess based on your old guess. So let your old guess be q. Then you can calculate a new guess, q prime. And your new guess will be 2 times q plus x on q squared, where x is the number you're trying to compute the cube root of, divided by 3. So this is a better approximation. Now, Violet, do you want to say how this will actually help us compute the real cubed root? Because this was only approximation. What can we do?
Keep doing it until we get to somewhere close to the actual answer.
Yeah, so if we can do this once, if we make a random guess and then we calculate a better guess, then we can take our better guess and get an even better guess. And if we take our even better guess, then we keep doing this over and over and over, improving our guess each time. Yes, Bruce?
How do we know when to stop guessing?
How do we know when to stop? That is one of the tricky problems in numerical analysis. So you could either do it after a number of iterations, or if you know a particular bound, you could say, well, maybe my guess, I only care about my guess within 2 decimal places. And once the second decimal place is no longer changing, then I know I'm close enough. But this gives us a problem. What's the problem? If I'm doing this method of waiting for it to converge, there's something Bell said before.
Do you not know what the right answer is?
We don't know what the right answer is, and it might not converge. Who said that? Josh. Yeah, so it might not converge if we're waiting for the guess to stop changing very much each time. So for example, if my guess is 0.13, and I say as long as the second 0.134, and I say as long as the second decimal place doesn't change, then I should just stop guessing. And then my next guess is 0.145, and then 0.172. The second decimal place is still changing and changing and changing, and so I'm not going to stop. It's only when I get 0.13 and then 0.13 again, and the second decimal place has not changed, that I stop. And so I run into this problem is if I don't get convergence, then I might run this infinitely. So maybe what we could do is we can combine our 2 different methods. So we could say, keep doing it until it converges, but with a limit of X number of steps. And if it doesn't converge after X number of steps, just stop and give me your best guess. So what we're going to do is we're going to iterate and generate q prime prime and q triple prime and q quadruple prime and try and detect when we're not getting any more accurate. So comparing the result from this iteration with the result from the last iteration, just as Bruce was asking about. And this gives us our method for cube root, croot.c, which is going to do exactly this. Now let's switch back to that. And you can see, it's still running. Pi has gotten a little out of hand here. We've probably run into an overflow at some point. So there is likely a mistake in my code. And I would love if someone actually tells me what it is later. That'd be super interesting. I guess I told n to go up infinitely, and so it will have overflowed at some point. Yeah, I don't know. Or maybe count. Count has probably overflowed. Yeah, count divided by n. So we've likely had some overflows over there, and I wasn't checking. Okay, let's go to croot.c. Finally, we're back to, this is actually an example that's typically shown earlier in the course, so we have some nice simple code to take us out. Enter a value, and then we call a function. And we've said the maximum number of iterations bounds, because we know that we have problems with floating point accuracy, and so we want to make sure that we don't exceed our floating point accuracy. And then we are making sure that we're not outside the accuracy bounds, and then just looping continuously. So let's try this. I'm going to replace everything on this line with croot. Oh, enter a value, and let's try 81. What's the cube root of 81? Yep, so we've got 4 point something there. What about, does someone know a good one to try? No one has a cube root they want to see? Come on. 57. Okay, and the cube root of 57 is going to be less than the cube root of 81, and we can see that we get 3.8. And what am I actually printing out? I'm printing out at the end the cube root, and then, oh, there we are. Printing out the cube root, and then actually doing the computation to calculate, to cube whatever the cube root was, and see how accurate we were in comparison to the number we asked for. So I asked for the cube root of 57, so it prints out the original 57, calculates the cube root of 57, and then cubes it to see what the result is, and we can see we're accurate as much, in as far as our computer has accuracy. So now let's try it with a really small number. Now if I look at what I get cubed, I can see the cubed value of the cube root that it returned has very little to do with the number that I put in. So I put in 0.01234556, and what it's given me out as the number that I originally typed in is 6.2109, so it doesn't seem particularly accurate. So again, numerical computation, super interesting field. This technique works great, but you're going to need to be careful about things like floating point accuracy. So we have one more demo for today, and this is one from physics. And unfortunately, none of my physics students that normally sit over there are here today, so they'll have to catch up on video. Let's say we have a spring, and we're trying to compute the force, F equals ma, and that is a function of a number of different parameters. The Hooke's constant of the spring, that's this value k, which tells us how springy our spring is. The damping of the spring, so if there's friction or something like that, or air resistance, how much of a fight is that putting up? How far our spring is extended when we begin, how heavy our object is, and how fast it's moving when we set it off. So you could say, let's say I pull the spring 3 centimeters. It's a very springy spring. Air resistance is low. I start off at velocity 0 because my spring isn't moving when I initially let it go. What is the acceleration of the spring going to be? And then using F equals ma, we can also do a whole bunch of other calculations. We can derive equations of motion, which then allow us to get the new position of the spring and the new velocity of the spring at a new time. And so assuming that we're willing to make very small steps in the amount of time, we can simplify and get these equations as a function of delta t, so the difference in the amount of time that's elapsed. Doing our simulation is actually going to be much easier than the page of math that physicists typically do, but they also use these simulations as a way of checking if their answers are correct, or even solving more difficult problems. So here I put in the spring constant, the damping force, the stopping condition. Remember, I have the stopping condition again because my numbers can be a little unreliable, or I only want to do this a certain number of times, because if the spring's going to bounce back and forth and back and forth and back and forth, and then it's going to make all these tiny jitters, and if the tiny jitters are going to take it beyond the accuracy of my floating point numbers, I'm going to run into problems again where it won't stop. I'll add a minimum and a maximum on the spring, so how large it can extend to, and just a scale for my graph. So let's not worry too much about that code, but this is where the real meat of it is over here, where I calculate the acceleration, I calculate the new position, the new velocity, and the new time. And all I'm doing in this loop is making very, very small changes and iterating this process over and over and over. And it turns out this will actually give me a pretty reasonable depiction of the spring's behavior. So let's quit that one and do our last demo for the day. So my spring, there we go. Okay, so I just needed to figure out reasonable parameters. So delta t is the size of the time step at which I'm going to examine this. So I'm going to examine it at increments of 0.1 of a second with a 10 kilo mass and starting out fully extended from the spring. So now we can see our graph is plotting the spring going back and forth until eventually it settles down. If I try this with a smaller mass, let's say a mass of 5 kilos, I can see that the springiness of the spring is more significant at the start because it's a very springy spring just dealing with slightly less mass. If I want, then I could do even smaller time steps and get a more hopefully a more accurate graph. And as I make delta t smaller and smaller, as I look at smaller and smaller time increments, my simulation is going to get more and more reliable. So this gives us our last technique for today. But there's also a whole range of things that you can do using simulation. You can actually find out the best way to play Monopoly by using this technique as well. And if you want a bit of fun, I encourage you to go and watch this YouTube video, which has a really cool discussion on comparing a theoretical way of solving Monopoly versus a simulation-based mechanism for solving Monopoly. And with that, I will catch you on Tuesday for our very last week of Foundations of Algorithms. Thanks very much. I'll see you then.